Okay, part 3 of chapter 7. Let's talk about average power. So average power is the rate at which work is done. We're talking about rate here. Okay, so and it is obtained by dividing the work by the time required to perform the work. In other words, P bar or P average is work divided by the time that it took the work to be done. So P is the work or the total work done on an object divided by the total time it took the work to be done. So something that we know is that the work is in the terms of joules, so it's energy, okay? And time is in terms of seconds. So you have joule per second, or what we call it as watts or W. Okay, as you can see right here, joule per second is watts. So the change in energy over time or joule per second will give you the watt, okay? The unit of power. Let's play with the formula a little bit. If an object is moving at a constant speed in the face of friction, gravity, air resistance, and so on and so forth, the power exerted by the driving force can be written in this format. So remember that we had P is W over time, and then I can write this W as the formula of it. So F dot D, okay, is the actual formula, and then divided by T. So if I can write this down as F D cosine theta over T, okay, and by the way, this is the cosine of the angle between force and displacement, and I write D over time velocity, remember? Do you remember this formula? X equals Vt plus x0, or delta x equals Vt from our second and third chapter. So in other words, if I want to solve this for velocity, velocity is delta x over t, right? This is the formulas for a constant velocity, right? This is for constant velocity. In other words, I have v here. So I can write this down as f v cosine theta, or I can write it this way, f dot v dot product, because velocity would have the same direction as the displacement. Something that we have to remember is this: velocity is always tangent to the path that the object moves. Okay? In other words, the angle between velocity and force and the angle between velocity and displacement would be the same. So it had the same cosine here. So I can write power to be work over time, or I can write it F dot V, the dot product between force and the velocity. So I can do that. This is an extremely important formula. Okay. So as you remember, the power is work done over the time that the work is done. Work is in terms of energy, so it has joule, and time is in terms of the units of seconds. So you have joule per second or watt. So joule per second is watt. So here's some activities, for example, running with 15 kilometers per hour, the rate in which you're burning, or a young 70 kilogram male is burning energy is 1,340 watts, or 1,340 joules per second. Okay? Sometimes we show it by kilowatt, and we say 1.34 kilowatt, okay, or 1.34 kilojoule per second. You can see different activities as the rate in which the energy is being burned. Time for work. Mike applied 10 Newton of force over 3 meters in 10 seconds. Joey applied the same force, so the force is the same, okay, over the same distance, 3 meters, in 1 minute. Who did more work? So let's see who did more work. F time D. F is 10 for both of them. 3 meters is the same for both of them. Okay, and that's 30. This time difference, 1 minute, which Joey did, and 10 seconds, what Mike did, has nothing to do with the amount of work being done. So both did the same amount of work here. Okay, Mike performed 5 joule of work in 10 seconds. So that's what Mike did. So I can calculate the power immediately, 5, or actually I can write it formula first. So I have 5 in 10 seconds, 5 joules in 10 seconds. So in other words, I have 0.5 of watt for the power. And Joey did 3 joules of work in 5 seconds. So Joey did 3 joules in 5 seconds. Okay, so we have 3 over 5, or 0.6 watts. Who produced greater power? Obviously, this is what Joey did. Joey produced more power because it's 0.6 watts. Engine power. Engine number 1 produces twice the power of engine number 2. So the power produced by number 1 is 2 times the power produced by number 2. It's just bigger. Can we conclude that engine number 1 does twice as much work as engine number 2? No. We don't really know because we do not have the information about the time. We don't know the time, okay? So since we don't know the timing of this, we don't know the relationship between T1 and T2. We don't really know. So we can't, understand or conclude anything here because we don't have the information about how much time it took them to do this work. Okay, electric bill. When you pay the electric company by the kilowatt hour, how are they actually paying for? What are they actually paying for? So you're paying for the energy that you're using, okay? But you're paying it in the kilowatt per hour. And the watt is in terms of power, so you're paying in terms of the power that you're using at your apartment or your house. So let's take a look at the summary. So if the force is constant and parallel to the displacement, work is force times displacement. If the force is not parallel to the displacement, then there is a cosine being involved, or FD cosine theta, as we know. The total force would produce the total work for us. Okay, so I can write it this way. I can write W total is being W of force number 1 plus W of force number 2 plus number 3, and so on and so forth. Or I can write it W total being the work done by total force. Okay, or F of total or F of net times displacement as a dot product, or F of net F of net d cosine of the angle between them. So SI unit of work is joule because it's the energy, and the total work is equal to the change in kinetic energy. This is work energy theorem. The total work done, or sigma W, or work total, is change in kinetic energy delta K, or K final, or K2, minus K initial, or K1. Where this K is kinetic energy, right? K is half mv squared. So work done by a spring force is this. Now, if this is the work done, and you're talking about the spring, you can consider this work to be negative if you are considering the work. So this is the amount of work, in other words. This is the magnitude of work. But we know the work done by the spring is negative because force of the spring is negative kx, okay? So the work has to be negative. And the way that we calculate this, if you remember, we had W is F dot dx, and W is negative kx dot dx. I bring the negative k out of this integration, so I have negative k, and I have x dx here, and then I have negative k x dx under the inside the this sign of integration, or if I integrate this, it will be half x squared, or I can write it down as negative 1/2 k x squared being my W. And if I want to find the power in which the rate of the work, showing the rate of the work for us, or the rate that the work is being done or produced, I have to divide the work over the time that it took it to do it, and it will give me the power. I can write the power in the other ways, and you have seen it in this video on part 3 that I can write the power as the linear product, or the product of the dot product of F times velocity, or I can write it as F V cosine of theta, which shows me that they are the same. The unit for power is watts, or joule per second. All right, so this is the end of chapter 7. If you have any questions, comment below, let me know, and I'll try to answer them.